In this video, I want to talk about the Cmos current source. Now recall that an ideal current source, the symbol of which is shown at the left, has a current versus voltage characteristic where the current is very flat for any voltage. So let's consider how we can make a current source using N-channel Cmos transistors. At the left, I have two N-channel Mosfet transistors. The transistor at the left has the gate connected over to the drain, and the drain connects to a resistor up to plus 5 volts. And this resistor sets the current in the transistor at the left. And in this video, I'm going to make some simplifying assumptions. I'm going to assume the voltage gate to source is 1.5 volts, and that the threshold voltage of the transistor is 1 volt. So in this situation, the gate to source voltage for each of these transistors is identical. And the current source is going to have a certain voltage at this drain output and a current ID. Now let's review the operation of the N-channel Mosfet transistor. Here I've drawn the cross-section for a typical Mosfet transistor, and I've connected the source node to ground, and I've connected the drain node to a battery that I call voltage V. And as I raise the gate voltage and increase the voltage gate to source, recall that I create an electric field under the gate, and that this electric field will attract electrons up towards a positive gate voltage. So when this gate to source voltage reaches the threshold, I start to get a channel region across here. And assuming that this battery voltage is 0 volts, the drain will also be at 0 volts, and the channel will be uniform, and it'll cause conduction between the drain and the source. Now, as I raise the V gate to source voltage higher, this channel is driven down deeper, and I'll exaggerate a little bit. Now, as I have a high gate to source voltage and I've driven this channel down, let's consider what happens as I increase this battery voltage and raise the voltage at the drain. So when the battery voltage is 0 volts, I'm operating at a point down here. This channel looks very resistive. And as I increase my drain voltage, I'll go up this curve, and I'll reach a point where it becomes relatively flat. It approximates a constant current, but not quite. And there's one important point, is this point right here. This is the point at which it starts to become a fairly decent current source. And let's examine this particular point. I'm going to erase this channel region. And as we raise the drain voltage, I may have a very strong electric field on this part of the channel. But as I raise the drain voltage, the electric field over on the right side of the gate becomes less and less. And if I assume that V gate to source is at 1.5 volts, and if I have a threshold of 1 volt, when this voltage at the drain becomes 0.5 volts, At that point, my channel is starting to pinch off at the drain region, and I have a gradient in the channel that looks something like this. And now I'm sitting at this point. And as I raise the drain voltage further, I move along this curve. And there's some slope here, because as I increase the drain voltage, this channel actually moves a little towards the left, and the effective channel length is decreased, and it results in more current. Now I can reduce this slope by increasing my channel length, where this is my channel length. So if I increase my channel length, I will reduce the current, but the slope will become flatter, which may be beneficial in some cases. So let's consider some simple mathematics. So say we want to calculate the voltage gate to source. How do we do that? Well, let's turn on this math equation. And this shows the equation for the approximate voltage gate to source that is approximately equal to the square root of this term plus the VT threshold voltage that we're assuming is 1 volt. And we're also assuming that this term, the square root term, is a half a volt. And that gives me the voltage gate to source of 1.5 volts, and I'm assuming in this particular example. So under the square root sign, we have 2 times a current, and that's the current flowing in our resistor or flowing in the drain at the transistor at the left. This W is a transistor width, and L is a channel length. And Kp is the constant that's determined by the fabrication of this transistor. So the foundry or the fabrication facility can tell us the value for Kp. So knowing Kp, knowing the width of the transistor, the length of the transistor, the current flowing in this resistor, and my threshold voltage, I can calculate the gate to source voltage. And notice that this point, or key point where it starts to become a good current source, is equal to the gate source voltage minus the threshold, and in this case is about a half a volt. So this voltage at the output can go down to about a half a volt, and still this current source can be fairly good. So now let's look at how we would do the layout of this particular set of NMOS transistors. This shows a typical layout for this current source. Now here I've added 2 additional N-channel transistors. So this part is our original current source that we examined previously. Now below I've shown the layout, and I've kind of color coded this. So the green is the gate electrode. And let's do some connections here. On the transistor at the left, this gate electrode is connected to this orange drain region corresponding to this connection here. Now the gate runs across the next 3 transistors here. This shows the W, or the width of the channel, and the L is the length of the channel, which is in the direction that the current will flow. Now my source regions are connected to ground, so this region is my ground. Now suppose I run, say, 0.1 milliamps or 100 microamps in this transistor at the left. Now, assuming that the drains of these 3 transistors are all at the same voltage level and at the same voltage level at this drain, then since my geometries, the transistor geometry and my bias voltages are all the same, that these transistors are going to have identical currents. So this will be 0.1 milliamps. This will be also 0.1 milliamps. And this will be 0.1 milliamps. So here I actually have 3 different current sources. Now if I wanted to make a current source that was 0.2 milliamps, I could just short these drains together and I would have a current source 0.2 milliamps. Now if I wanted to have a current source 0.3 milliamps, I could short this other drain, and now I've created a current source that has 0.3 milliamps. So you can see how the geometry relates to the current flow in these current source transistors. So let's consider now another way to make this current source. Now this is called a cascode current source. It's very similar. If you look at this region here, it's virtually equivalent to what I showed you before. But I've added some transistors in series. I've added this transistor and I've added this transistor. And so if we make the same assumptions as before, that my gate to source voltage is 1.5 volts and my threshold voltage is 1 volt, we can analyze the operation of this cascoded current source. And I'm assuming that my W's are the same for every transistor and my channel length is the same for each of these transistors, just to simplify things. Now if we analyze the voltage, we start at 0 volts here, and our V gate to source is 1.5 volts. So this is 1.5 volts. And we go up another V gate to source, which is going up another 1.5. So we have 3 volts at the gate of this particular transistor. Now we know that since all the geometries are the same, this voltage here, V gate to source, is 1.5 volts. So the key thing is that this voltage is more or less fixed at 1.5 volts. So I have fixed the bias point at this particular transistor. And this is a transistor that controls the current in my current source. So as I change the voltage here, this 1.5 volts stays very constant. So my current remains very flat. And that's the advantage of the cascode, is that this current remains very flat. I don't have as much slope. However, there's a disadvantage. If we look at where this starts to become a good current source, at this point, this is a higher voltage. Now, if I have 3 volts at the gate and I have a 1 volt threshold, when this voltage at this current source, at this drain, is equal to 2 volts, I start to pinch off the channel in this transistor, and I start to go into this region where it's no longer a good current source. So I want to avoid operating in this region here and operate over here. So again, the advantage of the cascode is you get a very uniform current, but you sacrifice some voltage margin.